I want to discuss some big problems like Ithaca conjecture and things like that. So we need the notion of the positivity of direct image shift. So given a vibration f from x to y, so this means a morphism with connected fiber, surjective morphism. So I forget the word surjective. So this means a surjective morphism with connected fibers between smooth projective manifolds. So yes, so it is a natural to try to relate the positivity properties of the local total space and the base y and the general fiber f. Okay, so an important problem in this context is Ithaca CNM conjecture. This is an upper problem, and that predicts the subadditivity of the Kodaira dimension. So more precisely, the CNM conjecture states that the Kodaira dimension of x is bigger than the Kodaira dimension of y plus the Kodaira dimension of f. Okay, so Ithaca posed this conjecture. Some people did some progress, and some cases are known, but some cases are not known. Okay, so it turned out that one of the main issues in the study of this conjecture is the discussion of the positivity of direct image shift. Okay, so Kawamata, Vivek, Kohler, people like that construct some method. So they attacked the problem using the positivity of direct image shift. Okay, and this problem or this conjecture is related to MMP. So if you can resolve this conjecture, so this is closer to MMP in some sense. So we can resolve MMP for a dense case. Okay, so yeah, so first Fujita proved this result. So he is a Japanese mathematician. So if f is a vibration, but the base here is a curve, so this is a special cases. Okay, the base is not a varieties of higher dimension. So then he proved that the direct image shift is locally free, so is a vector bundle, and it is NAF. So I remember, what does it mean, NAF? NAF means that we take projectivization, we take O1 of this. So if O1 is NAF, so this is NAF. And this, we can see that NAF in this case can be described as so we can say that vector bundle is NAF on curve if and only if so the degree of this vector bundle is positive. So the degree is defined by the integral of the first class shell. Okay, and the degree of any quotient is also positive. So for example, we can take CP1 so as a basic case. We take C is equal to CP1, and we take as a vector bundle O1 plus O1, for example. So this is NAF, and okay, this is ample, but okay, take O1 plus the trivial bundle. This is NAF because the degree is equal to 1, and we take any quotient. So the quotient will be so there is two cases of the quotient. So O1 plus the trivial to O1, or O1 plus the trivial to the trivial. So in the both cases, so the degree is positive. So this is NAF. And for non-F example, you can take O1 plus O minus 1. So this is not NAF because there is this contribution of O minus 1. So because when we take a quotient to O minus 1, so the degree of this is minus 1. So this is not NAF. Okay. Okay. So Kawamata and Vivek generalized this result when the base is of higher dimension. So Fujita proved this result when the base is of higher dimension, and when the base is a curve, and Kawamata Vivek generalized the result when the base is of higher dimension. So they remarked that the singular locus posed some problem Because here we assume we assume nothing about the fibers. Okay, so we take just a vibration, not a smooth vibration, not a submersion vibration. So the fiber can be singular. Okay, so for when the base is of higher dimension, so Kawamata weaving see that the singular locus of the fiber is a problem. Okay, so they prove this result. So you take a vibration between smooth projective manifold and D be the F singular locus. So if D is a normal crossing divisor, so we assume we see that we assume always this normal crossing properties, because we need to define some metrics to prove neffness. We need to define some metrics, and we need to extend this metric in the singular case, but logarithmically. For example, extend the D-line connection, extend the connection as in D-line sense, etc. So we need this normal crossing. Okay, and outside the codimension 2 sets, the fiber are reduced with normal crossing. So the fiber are not multiple, and they intersect like this. So they prove that the push forward or the push forward is locally free and neff also. So we can see that here Kawamata weaving discussed the singular locus, because if we didn't discuss that, we cannot say a result like that. Okay. So more generally, if you don't assume any condition of the singular case, as I said, we can still have positivity result, but not a neffness. Okay. So if you take vibration between smooth projective varieties, so then the direct image sheaf is weakly positive. So this notion of weakly positive is weaker than neff, because here we didn't assume the positivity properties. And the more generally, when we take a tensor with this relative canonical divisor and times, so the push forward is also weakly positive. Okay, so here weakly positive means that we can see that weakly positive for me means that is neff restricted in every curve. Okay, but mathematically is not that, but we can see okay, so mathematically means there is an open set such that the symmetric product of this push forward twisted with any ample line bundle is neff. Okay, so by the work of Kawamata weaving, this settled the CNM conjecture of vibration was general fiber is of general type, or the base of is also of general type. So here we see that general types varieties is like a good varieties, because we can prove some things, and because we have a lot of section. Okay, so by the work of Kawamata, so CNM conjecture is true when the base is any curve also. Okay, and for further application, example MMP for a log pair, and we know that a log pair is important because we want to finish MMP by induction. So it is important to produce more general version of this theorem. So given a vibration of the line bundle on X, one can ask for the positivity properties of the direct image, so push forward of the relative adding a divisor or a line bundle. So there are some results where L is neff and relatively big. So thanks to Kawamata weaving. So yes, so there is a result called Kawamata weaving vanishing theorem. So we know that in complex geometry, there is a very fundamental result called Kodaira vanishing theorems. So it means that the cohomology group HI, if E is strictly positive, for Kx plus an ample is always 0. Okay, so Kawamata weaving generalized the situation for neff and big. So neff and big is weaker than ample. So neff plus big. So if the divisor is neff plus big, so this is weaker than ample. And we prove the same theorem. And this is very important for MMP also. Okay, so now we see the last progress based on Demai school or the student of Demai. So Paul is a student of Demai, but Berson are just a collaborator of Paul. So Berson and Paul Takayama generalized the result when the case is L is pseudo-effective. So pseudo-effective means that the limit of effective or this divisor is in the boundary of the effective cone. Okay, so what he proved, so why I say thanks to Demai, because Demai proved that if L is pseudo-effective in the algebraic sense, so there exists a singular Hermitian metric on on this line bundle, such that the curvature is positive. But here the curvature is not defined in the usual sense because the metric is singular. So we should take a current. So we define curvature as a current. Okay, so this is a famous result of Demai, but Demai has a lot of important results. Okay, so here the theorem of BPT, so Berson Takayama. So he proved that if you take vibration, so we take L pseudo-effective, and as H any singular, so a singular metric, such that the current positive, and always we can find that by Demai theorems or Demai result. So then the push 4 is weakly positive. So this is so here we weaken the condition on L, and we have the positivity of the push 4. Okay, and here, but we should twist with the multiplier radial shift. So what does it mean, the multiplier radial shift? So here EH. So this means that the section of L, which are L2. So this means that we take the integral of this section locally, so twisted with the exceptional -2 phi. So because every metric can be written at the exceptional minus a y. So here we take a y. So if this so the section of this divisor L times the multiplier ideal shape are always L2. Okay, so this is analytic approach, and this is more general picture. And so based on this theorem of BPT, so I studied this direction 3 or 4 months ago, and I give some presentation on that. So very detailed presentation. Okay, so based on BPT theorem and Demai approach, Julien Sao is a professor now at Nice University. So proof CNM. So Julien Sao is a student also of Demai. So he proved CNM conjecture when the base is a surface, because we know that when the base is a curve, so CNM conjecture is true. But otherwise, we don't have a result except of general types. So he proved CNM conjecture when the base is a surface or an abelian varieties, or more generally when the base is of maximal Albanese dimension. So the Albanese dimension, Albanese map is surjective. Okay, so this result of Julien Sao is very, so his paper is very, he has 2 or 3 papers on that, and are very hard to so motivated by negativity conjecture. So my recent work was on fibered surface. So now I want to discuss my results for 10 minutes maybe. So let X be a smooth projective surface and C be a smooth irreducible curve. So we state the following conjecture. So this is known as negativity conjecture. So what is the statement? So there exists a constant M depend only on X, on the surface X, such that for any smooth irreducible curve, we can have a lower bound for the self intersection of C2. okay, for any surface. This is very difficult conjecture. So I wanted to study this conjecture in some cases, and okay, so here there is some slide or some discussion based on my previous note, but this is not related exactly on my work. This is very very fundamental as a discussion. So I try to discuss the conjecture case by case, but the hard case is the problem. So let me show you some details. So for example, if there exists a positive m such that the linear system of minus mkx is not empty, so this means that this divisor is effective and there is a section. So I say that the conjecture is true. So because by Genius formula we can have we can see that all the self intersection of C is bigger than -2. So there is uniform bound depend only on the varieties. So yes, we resume the situation. So if for example, if the variety is Fano or projective space, so this is true in some sense. Okay. Okay, I can skip this this discussion because this is not related to my work. Okay, so I said that because here in the slide there is lot of question which is not known. For example, in the case when okay, in the general type varieties, so the conjecture is very difficult because we cannot find. I say that if we can find an uniform upper bound for kx times c, we can find the uniform lower bound for c squared based on Genius formula, and this general types is surprising because. This is the very hard case for this negativity conjecture. Okay, I want to so I wanted to study the problems using another approach and like a fibered surface. So the problems is for surface, but we know that if we can solve the problems for fibered surface, we can solve for surface, because if we take a pencil for any surface, so pencils means two effective divisor, it means two section. So by this two section, we can construct a map from this surface to CP1. So this is fibered, okay? And if it is not a morphism, it is rational, we can take finite sequence of blow-ups, and we can find a model such that so the map is defined everywhere. So yeah, so I wanted to study the problems differently. So here we consider a vibration from smooth projective surface to a smooth projective curve. So we take an arbitrary divisor such that the rank of the push forward is bigger than 1. So this means exactly that there is at least two sections in the fiber, because the rank of the push forward is defined as the dimension of a set of section fiber-wise. Okay. So okay, let's see after what happened if the rank of the push forward is equal to 1 or is 0. This means that the push forward is 0. So there are no sections in the fiber. So okay, so here N1 is the Miyawka divisor of the maximal destabilizing subvector bundle. So this definition is the definition 3.3 in my preprint. So what does it mean, the Miyawka divisor? So for this push forward, we can take a correspondence between this push forward and the linear system of D. So we know that the linear system of divisor is divided into parts, a fixed part and a movable part or moving part. So what does it mean, fixed part? This fixed part is in all the divisor is contained in all the divisor of the linear system, and this Miyaoka divisor is defined as a moving part minus some constants times a fiber, and this constant is related to the stability of the vector bundle. So this is like a very important divisor because it relates the positivity and the stability of the push forward, slope stability. Okay, so okay, here I mean N1 is the Miyaoka divisor of the maximal destabilizing subvector bundle. So we take Harden-Arisiman filtration of the push forward. So this is a filtration defined as so sequence of subshift of the push forward, and all the quotient are semi-stable, slope semi-stable. Okay, and this the first one in the section in the sequence correspond to this divisor N1. Okay, so my results. Okay, we can go directly what we proved. Okay, so what we prove here, we prove that if D is a NF divisor, okay, and the final slope is positive, that means that the push forward is also NF as a vector bundle. So there is an equality between the positivity of D and the positivity of the push forward. So we have a relation between two quantities. One is the self-intersection of D. So D is in the total varieties, and the push forward is a vector bundle on a curve. So we relate two things, one in the total and other in the base. And this is related with some constant, and this constant describes the geometry of our vibration and our divisor. Okay, and why we have result like that, and what is my motivation? Because as I said, I want to study negativity conjecture. That means that we find a lower bound for the self-intersection of any curve, and by this result we can see that the problems translate to study the positivity of the push forward for any curve. So for CP1, for example. So it's like we simplify the conjecture in some sense. Okay, so the conjecture, if we find the lower bound of this degree of the push forward, so the conjecture is true. Okay, and I described so we have different inequalities, and it depends to the geometry. So for example, if the final slope is negative, that means that the push forward is not NF. So there is some negative part appears in this vector bundle. So and for example, there exists a NF subshift or NF subvector bundle. So we have so the inequality is translated to study the degree of this subshift, so etc. So by this result, I deduced the famous Shao-Gang result. Okay, so what he proved, Shao-Gang, so F be a relatively minimal vibration. So that means that there are now -1 curve in the fiber. So and the fiber has genius bigger than 2. Okay, and if we take in my result D is equal to the relative canonical divisor, so this is like a natural choice. So the square intersection of this relative canonical divisor is bigger than 4G minus 1 over G times the degree of the push forward. So and we see that this constant G minus 1 over G is related to our vibration because it's the genius of the fiber. Okay. So as a consequence, I proved that the result of Shao-Gang is not optimal if we add some geometry condition on the vibration. For example, if we take the same assumption, okay, of Shao-Gang, but we take so this Miyawka divisor, which relate the stability restricted in the fiber, is not special. So that means that H1 of this divisor is 0, and this is a dense case, so always can be happen. Okay, and there is at least 2 sections for this Miyawka divisor restricted in the fiber. So if these conditions are satisfied, we have better than Shougang, and the inequality. So this constant is more better than the inequality of the constant of Shougang. Okay, so many thanks for your attention. This is all for now.